The following video will outline the physiological variable of interest, outline how the Doppler ultrasound measures this variable, how the ultrasound is set up, and the limitations of the equipment. Many of the studies within the Human Vascular Control Laboratory are interested in changes of forearm blood flow in relation to different protocols or stimuli. To determine what influences forearm blood flow, we must first understand what blood flow within the human body is influenced by. Blood flow is proportional to the change in pressure gradient across the vasculature multiplied by the conductance of the vasculature in which blood is traveling through. Blood moves from areas of high pressure, i.e. arteries carrying blood from the heart, to low pressure, i.e. veins moving blood to the heart. This movement from areas of high pressure to low pressure is what creates the pressure gradient across the vasculature. Conductance, or K, is the resistance met within the arteries, such as vessel diameter. For example, a dilated blood vessel would result in decreased resistance and therefore greater blood flow. Therefore, the two main variables that could influence blood flow is the change in pressure gradient or the conductance. Doppler ultrasound uses the concept of Doppler shift to measure blood flow velocity. This is the change in the frequency of sound waves that occur as they are reflected off a moving object. Doppler ultrasound can estimate blood flow within the vessel of interest, which is the brachial artery in this case, by measuring the rate of change in its pitch or frequency. This is done by placing a flat probe to the skin over the brachial artery, while the transducer emits a high-frequency sound wave. These sound waves are then reflected back to the probe, which enables the user to graphically visualize the velocity of blood flow. Within our lab, forearm mean blood velocity is measured using a 4 MHz pulsed Doppler flat probe. This is securely fixed to the skin over the brachial artery above the antecubital fossa of the exercising limb. To obtain the measurement with minimal error, probe inclination angle relative to the skin should be around 45 degrees, with the brachial artery approximately parallel to the skin surface. A key aspect of this setup is that the ultrasound probe must be kept in constant contact with the exercising limb throughout the protocol. The current images shown were taken when the participant was at rest. During rest, blood velocity remains fairly constant. The highest point on the peak indicates the maximum velocity, while the lowest point on the trough indicates minimum velocity. As you can see, during rest, the graphical representation of blood velocity stays constant, with the amplitude wave being quite small. As you increase the amount of work that must be done, the blood velocity will increase as more blood must be delivered to the exercising limb. The current image was taken when the participant was contracting at his maximum capacity. As you can see, this is very different from the at-rest measures that were shown earlier. Blood velocity is slowest during the actual contraction, as the maximum contraction creates the local pressure within the artery that temporarily slows the blood flow to the exercising muscle. Blood velocity is greatest between contractions, as blood is able to flow from areas of high pressure to low pressure. Although a strength of using Doppler ultrasound is that it is a non-invasive procedure, there are a few limitations to the technique. For example, the probe is only sensitive to one velocity component. As such, velocity within only one vessel can be calculated or measured at a time. In this case, the velocity component that was measured was within the brachial artery. Another limitation of this technique is the motion artifact noise that may affect the clarity of results. This is the blurring of reflected sound waves that may occur due to respiratory, muscular, or other movement of the subject during the protocol. This highlights the importance of finding the correct angle in which to place the probe, as it is very sensitive to motion.